We talk about tensors, quantum entanglement, and
great. Thanks so much for having me. Exciting things happening outside. That's a nice place for the group. Yeah, it's really great to be here. Good to see all of you. Thanks for the invitation. Some of us saw each other last week. I suppose this will be a different talk, so it will not be boring. I want to talk about well, tensors, of course, as befits this workshop, from the perspective of quantum entanglement, also algebraic complexity theory. And we'll also see optimization, but it will be a different kind of optimization than what we have seen this week. So it will be convex optimization, even but on curved spaces, not in the Euclidean setting. So hopefully that will be interesting to you as well. So it will be a bit of a melange of algebra, quantum, complexity theory, optimization, and I hope you'll enjoy it. So I want to start my talk by discussing, well, I guess my motivation as a quantum information theorist for studying tensors, which is that I think of tensors as quantum states. We saw that already in several talks, for example, a long talk this morning. So a quantum state of d particles, subsystems, parties, laboratories, if you like, you can describe by a vector in the tensor product space, Cn1 up to Cnd. So I will draw always draw these pictures like here. I will try not to put cats around it. So the cats are these little flags that physicists like to use to signal that it's a vector. If I do, you know what it means. Okay. When we deal with these tensors, there's of course many things we can do with them. We can take many of them, contract them, and so on. One other elementary operation that we saw already in the talk today was to transform the tensor. Okay? And because there's this tensor structure, the fact that it's not an unstructured vector space, but a tensor product of smaller factors, a natural class operation is one that preserves the structure. Okay? And so in the physics context of the old school term for this SLOCC, for stochastic local operations and classical communication, or local filtering, the algebraic folks call it restriction. We saw that this morning. Basically, you take a bunch of matrices, one for each tensor factor, and you hammer it on your tensor T, you get a new tensor S. So you could visualize it like on the picture here. So that's a natural class of operations from a quantum perspective, because in a way, it does not create entanglement. Well, certainly does not create non-product states out of product states. Whether it really does not create entanglement depends a bit on your perspective. That's because there's different such classes and restrictions on these operations you could place. The S, the stochastic, and the S of SLOCC, it stands for probabilistic conversion between quantum states. So you do local operations, maybe you measure your particles, and then you get to post-select on a desirable outcome. So it could be that that's an outcome that may, maybe in a different sense of the word, increase the entanglement, but we'll not worry about this. So from a quantum perspective, again, the tensor factors, they correspond to parties. For example, here there are 3 parties, the dimensions n1, n2, and c. Okay. Now, we also saw this morning and in other talks that it's often interesting to study not only these degenerations, where you hammer a fixed set of matrices, but to allow yourself to take limits. Okay. If you allow yourself to take limits, then you can just as well keep these operations AI to invertible matrices, because in the limit you can anyways make them non-invertible. So that leads us to a natural group action, the tensor action by this product group GLN1, GLN2 times, and so on up to GLN. Okay. And so an element in the closure of that orbit, I will, well, people call it degeneration. Okay, so it's a sequence of matrices of this form, such that if you hammer them on T, then the limit point is S. Okay, it's the boundary of the variable T that is mentioned. So with this setting in mind, one can now ask several questions. For example, could ask, are there nice normal forms for these tensors with respect to this operation? So I'll give you an example of what could mean by such a normal form. When is such a conversion possible? Okay, that's a question that arose well, in both talks this morning. How about conversion rate? So if you have many copies of one tensor, and you want to get as many copies of another tensor out, okay? What's the optimal rate? That's, for example, also relevant in this tensor network setting. And then how about algorithms that allow us to answer these questions? Okay, so that's sort of motivating questions for the talk. So if we think about 2 tensors, so matrices, right, we can apply left and right operations to bring the matrix into a very simple canonical form that has a bunch of 1s and a bunch of 0s in the rest of the matrix. So right by Gaussian elimination, if you like. Or the left-right action, which corresponds to the tensor action if you think of your matrix as a 2 tensor. Now, if you go to higher tensors, you could say, well, why don't we do a similar thing? For example, I could take a tensor, I could flatten it. Now I have a matrix. For example, I could flatten it one tensor factor versus the rest. Okay. Now, of course, on one side, I have the full GL and J, if it's the J's tensor factor. On the other side, though, I have a subgroup. So I can probably not reach this form exactly. Okay. But you could hope for a simpler thing. For example, you could still hope for the singular values. You could try to make the singular values of these flattenings flat, uniform, all ones, okay? Or as many ones as you can get. Okay. And so to make that precise, I want to introduce the notion of the reduced state or the quantum marginals, maybe more pictorially of a tensor. So what you do is simply, I mean, there's different descriptions on the slide. So one idea is the following. Suppose Sj is the J's principal flattening. So flattening, you take your tensor, you think of it as a matrix from the J's tensor factor versus the rest. Now you can compose this with its Hermitian adjoint, denoted as J star. That thing is a positive semi-definite operator on NJ, C and J, right? You go from NJ to the product of all the other dimensions, and you go back by the adjoint. So the singular values of the flattening are, with respect to this cut of this principal flattening, they're captured by the eigenvalues of that matrix. Okay, and if you want to make them all flat, it means that this should be the identity matrix. Okay, this positive semi-definite matrix. And so if you think about it pictorially, so what you do is you take a tensor, then you think, say, this blue index, if you can see it as the J's index, you flatten it. So you think of the blue index versus the rest, and then you contract it with the adjoint. So maybe there should be a complex conjugate here. If I draw things reverse around, I always conjugate in my head. And so this contraction of all the indices except for the J's one, that's just the matrix multiplication in Sj star. So the big dimension, the product of all dimensions except for the J's one. And so this object here has two dangling indices, a covariant and a contravariant one. So that's a matrix. Okay. It's a positive matrix because that's one can see from this formula or from this factorization. Okay. So those objects, they describe the quantum state of the J's particle. But from the perspective of normal forms, you could just say, well, that's an object that captures the singular values. We want to make the singular values flat. I want this guy is equal to the identity matrix, proportion to the identity matrix. Okay. And so Frank, many years ago, as before some of us were born and others went to quantum kindergarten still, he proposed this, a normal form based on this idea. Maybe he had more nuanced reasons for coming up with this, but this is what they did. Okay. So in the language here, basically what they propose, if you have a tensor T, then let's say a degeneration, so something in the orbit closure of that tensor S is a normal form if all of these marginals, these quantum marginals, are equal or proportional to the identity matrix. So that's the definition. And it's a sort of a basic factor of geometric invariant theory that this is a unique up to unitary transformations, in the same sense that the singular values do not determine the matrix, but it determines this up to unitaries on the left and on the right. So, so that's what they proposed, and they even gave an algorithm. It's very simple, and basically the idea is it's very simple to make for any fixed J to make the J's marginal flat. If you look at this picture, basically what you do is you imagine, well, you want the matrix that this picture is the identity matrix. So what you do is you simply left and right, you multiply both these indices with the square root of the inverse square root of sigma J. Or from the perspective of this matrix, which is sigma J, you just left multiply by inverse square root of sigma J, and you right multiply inverse square root of sigma J, you get the identity matrix. So that's what I try to write here as maybe in a more standard way. Okay, so this is like acting by the inverse square root of the J's quantum marginal. And if you think of S as being flattened, right, it's exactly acting on the small dimension of the flattening. Okay. And so the Gra matrix therefore becomes the identity. Of course, this only works if that's full rank. If it's not full rank, you can never achieve this normal form of rank. So that's kind of necessary to do it. And they propose this algorithm, and so basically they propose just sweep through. Okay, do it for J equals 1, J equals 2, 3, 4, and start again. Okay, and they could show non-quantitatively that this procedure converges under some hypothesis. I'll come back to in the next slide. Okay. And in fact, I mean, they invented this algorithm, but in a different community had existed, actually in several communities had existed before for different reasons in a different language. So in statistics, for example, it's known as the flip-flop algorithm. I'll tell you, I mean, it's clear why it's flip-flop. It's the flip-flop thing. If you have two tensor factors, and then if you have more, then there's lots of flopping going on. Flip-flop flapping, I don't know. We analyzed this algorithm later. I'll tell you about this in a second. We called it tensor scaling, and only afterwards understood that it was also in there. But sort of the question that arose here, right, is like a very nice proposal, but what does it mean? How fast does this algorithm converge? Okay, so it probably does converge in the sense that if you don't make progress, you're done. Okay, but it was not quantitative. So that's what we set out to do, and it sort of took, I guess, 15 years after the invention of this algorithm to do this analysis. Okay, this is a joint work with several people, starting with Peter Bruegge and ending with Arvid alphabetically. So here's again the iteration. Okay, this is of course an instance of applying this group action by this product group that will be always the G I use, and I also recalled it for you here on the board to remind you of the notation. So what we could show is that to find, if you start with a tensor T and you want to find a tensor S in its orbit, okay, such that all the quantum marshals are close to the identity, epsilon close. You cannot in general do it in one step. You have to degenerate in general, so you can only get as close as you want. Okay. Then a number of iterations of this of Frank's flip-flop algorithm suffices that is polynomial in the input size, so the dimensions, and also the bit size of the entries of the tensor, and 1 over epsilon. Okay. So we are happy about the first part, not so much about the second, but it's at least it's what one can expect for these kind of first order algorithms. So I want to tell you a little bit how this works. What is the idea behind this? Both the analysis, the sort of non-quantitative analysis in the previous paper, and what we did there some 10 years ago. And the basic idea is that these iterations secretly minimize a function. They successively minimize a function. And the function you could write down like this, hopefully modular type. So it's a function on the group if you want. And each, right, you can imagine like each update step, it gives you a new group element, right? You have your current scaling, sometimes we call it, and you update the J's scaling by left mod 1 by sigma J minus 1/2. So the objective, roughly speaking, is the following. It's almost the norm of the rescale tensor, except that you want to make the transformation determinant 1. Okay. You can see later why that's a natural thing to do. If it's determinant 1, though, you may see that, for example, if you like invariant theory, geometric invariant theory, right, everything's a null cone for the GL action, but not for the SL action. So, for example, the notion of semi-stability that many of you will know is interesting for the SL action in that case. Okay, so that's why it's interesting to do this. And so, indeed, this is an element in the orbit of T with respect to the restriction of the action to the determinant 1 subgroup. And if your tensor is semi-stable, it means exactly that you cannot go to 0 with this procedure. So this function, the infimum of this function is always bounded from below, strictly above 0. Okay? Infimum is strictly positive. Okay? And that's exactly the hypothesis under which this algorithm works. So what you can imagine is that each step of the algorithm, it decreases this function, it gives you a new G prime that is smaller, but you can never go all the way to 0. So if you take a convergent subsequence, you still get a non-zero tensor in the limit. And that tensor is then in the orbit closure, and it's a non-trivial tensor that has its marginals all proportional to the identity matrix. Okay. So that's how it goes. So maybe two more things about this. Also maybe to explain the determinant here. So I don't want to explain the calculation detail, but I want to tell you that the key ingredient for, let's say, if you don't worry about quantitative iteration bounds, but just seeing why things decrease, it follows from the arithmetic geometric mean inequality. If you think about this norm square, so what it turns out is that if you make these marginals to the identity, so this iteration makes the J's marginal to be equal to the identity, then the norm square of the new tensor, if you don't do this determinant nonsense, it's the same as the trace of the marginal, and the trace of the identity is nj, right? It's the j's dimension. Okay. Now, if you add this determinant, then that's the only thing you change, right? So basically, the only change on this norm the norm will be nj times whatever is the value square of this determinant. Okay. And so the determinant that's the value square of this determinant for gj equals this choice here, right? There's a minus, there's a plus, there's a 1/2, but there's a square of the norm here. What you get is the determinant of the margin to 1 over nj. Not important to verify it, but this is the geometric mean the eigenvalues of the marginals. Okay, and the geometric mean is less equal to the arithmetic mean, so the ordinary sum, right? The average in the ordinary sense. And that case is bound. Okay, so the arithmetic mean, geometric mean inequality tells you that the new f is less equal to the old f. So that's what Frank observed. And then you can make that more quantitative by more quantitative versions of this arithmetic geometric mean inequality. Yeah. I know it's exciting, exciting times. Now, to make these things quantitative, okay, one needs a quantitative version of this bound, and also one has to quantify this object here, right? You're minimizing a function, one coordinate at a time. It's called coordinate descent. You have to know how small could it possibly be in order to control how many iterations. Right? It's like to control the iterations, you need to ensure progress. That's ensured by AMGM, and that you have to know how many steps you have to take at most. How small the function can be at most. And for that, we actually use constructive invariant theory in some sense. Let's say that the fact that the invariants don't have too high degree and are not too complicated, don't have too large coefficients, allows you to control this object. Okay, so it's a nice interplay between analysis and. All right, so that's just maybe for if you want to know the details. So what do we learn from this? And why did I tell you about this perspective on this algorithm? Well, for one, we know that if the format is nice, and we had this discussion yesterday, for example, if all the dimensions are the same, the generic tensors are semi-stable, so generic tensors have such a Frank et al. Normal form, okay? Also, it turns out that the same algorithm can, sort of thinking about it the other way around, also be used to test semi-stability, okay? Because you can sort of, intuitively, you can run this algorithm, and either your norm becomes smaller, goes to 0, then you're in the null cone. You just proved it in some sense, or you don't. Okay, and then you must be semi-stable. So that's so somehow you can solve this algebraic yes/no question, discrete question, by running this gradient descent or this minimization type algorithm. So that's maybe of interest for the algebraic forms. Okay. All right. So one question one could ask here is, can we similarly optimize norms for other actions? So here we took as a simple action the tensor action GLN up to ND on the space of complex tensors, D tensors in this case. In principle, maybe you can come up with similar iterations for other actions. You could ask, is this good for anything? So I want to briefly tell you two and a half examples that are not that are different actions, but maybe that you find interesting. The first one will be very high level. Okay, so one other situation where tensors arise is in statistics. Namely, if your data itself is tensorial. So if your data is, for example, matrix value. Okay, so it's a bivariate data. Then one can make different structural assumptions. For example, one can make the assumption it's, we always assume things are Gaussian, but we could assume, for example, that the covariance matrix of our Gaussian is a Kronecker product of smaller covariance matrices. That's called the matrix normal model. It's a Gaussian model. It's an assumption a bit like in the spirit of a sparsity or low rank, but it's a structured model. Okay. So I'll come to that in a second. So imagine you have a bunch of samples, tensor variate samples, okay, T1, T2, and so on. Then, of course, you can connect them into a big tensor tuple. Okay? So even if P is 2, that's interesting because now a tuple of matrices, not a single matrix anymore. I wrote R here just because that's folks like real Gaussians and real, but it doesn't matter at all for the discussion. You can think of this tuple of tensors also as a tensor with one more index, right? And that additional index that carries the index into your data set, if you want, or into your samples. But you will never act there, okay? So it's just a proxy, but you can think of it as a single tensor as a tuple of one dimension lower, one rank lower tensors. Okay. So now it's easy to see, but we will not see it, we will not compute it, that if you make the structure assumption that your samples come from what's called, again, the tensor normal model, a normal distribution, center normal distribution, where the covariance matrix itself factorizes, okay? So again, that's called the tensor normal model. Then maximizing the likelihood for that model, which is something you would do. It's basically maximizing the probability for fixed samples, but as a function of the sigmas, right? And you want to find the most likely covariance matrices. It turns out that after some manipulations and up to some slight lie, that's exactly equivalent to minimizing the norm of this tensor tuple with respect to this action, not acting on the multiplicity on the sample index. Okay, so it's D1 up to GD times identity. You don't do anything here. Okay. So just a little transformation, log likelihood pulls, right? There's the Gaussian quadratic in the exponent, the exponential gets rid by the log in the likelihood, and so that one. So the same algorithm, okay, the same flip-flop algorithm computes the maximum likelihood estimate for these Gaussian models than what Frank et al. Proposed for finding normal forms of quantum states, okay, tensors. So that's kind of fun, maybe. Another sort of light, well-went sort of application that I guess we already saw, though, so several times, is another area where tensors appear is, of course, in defining tensor networks. Right, we take one tensor, we maybe copy it many times and contract it in some way. So we saw those folks already this morning. So these are the one-dimensional, PEPs or matrix product states. Similarly as before, we think of the 3 tensor as a tuple of matrices, if you want, or just as a 3 tensor. Now the 2 indices, one is the space and the other is the dual space. So we can contract in a canonical way, right, by just putting them to each other and contracting each V, which is V star. Okay. Here I put what's called periodic boundary conditions. Okay. These objects now are quantum states for every n, right, which dictates how many copies I take. I get one quantum state in an exponential in n large Hilbert space, all parameterized by the single 3 tensor. Okay. So Angela discussed this morning more complicated versions of this ansatz. From this algebraic perspective, the quantum states, or if you feel unhappy about vector-valued functions, the coefficients of the quantum state are invariant polynomials for the simultaneous conjugation action of G and N on this matrix tuple. If you take your matrix tuple here and you act by G on the right and G inverse here, that of course preserves this object, right? Because you have G inverse, G inverse all the time on the bonds, right? Like the right G of the previous tensor and the left G inverse from the next tensor. Okay? And because of the boundary, periodic boundary, like it works all the way. So you can think of the quantum states actually as invariant polynomials for this action I wrote down here, for the simultaneous conjugation action. And so in the spirit of Strata and friends, you could now say, let's define a canonical form by minimizing norm, okay? Just with over the orbit of this group action. And it's amusing that this, canonical forms for matrix product states are extremely well understood. There's people use them routinely. This is a different one. It's more complicated to compute. It's again computed by a flip-flop type, sort of a minimization type iterative algorithm, unlike the usual one, but it shares many of the same features. And one thing that's maybe amusing is that it directly makes sense also in higher dimensions. Okay. So that's for maybe the tensor network folks. So in higher dimensions, right, instead of having one ingoing, one outgoing virtual bond, we have, let's say, horizontal and vertical ones, different Hilbert spaces. The group action is G inverse, H inverse, so 2 different GLNs. It's like, you could call it multi-conjugation. It's like conjugating horizontally and also tensor with conjugating vertically. G inverse, H inverse. Not acting on this bottom one, which is the one where then the quantum state will live, the tuple index. Now, similarly, invariance here, you can get, well, for example, by taking a grid of tensors and putting the tensors contracting horizontal out with horizontal in and vertical out and vertical in. But you can actually do more. You can, for example, also insert a little twist if you want. You can permute indices, for example, at the top before you contract them with the bottom. So this something that you could not interestingly do in that case. If you do analogous things in MPS, then you just get a product of 2 of such pictures and they decouple. Somehow in one dimension, all compact manifolds are sort of unions of circles. In 2 dimensions, there's interesting surfaces, there's non-orientability, so you can think of this as like twisting a little bit. That's a bit the intuition I don't know. Okay? But still, you can apply these things and you get a normal form and what's called a fundamental theorem in this community that characterizes, from this corresponding group action that characterizes when do 2 tensors give the same quantum states, not just on all square grids, that turns out to be an undecidable problem, but on arbitrary contraction graphs along this way. You can think about a square grid with arbitrary boundary conditions. So you can permute before you glue. Okay. Those generate all the invariants. All right, then the other thing we already mentioned, maybe for the invariant theory folks, it's interesting that for very general class of group actions, one can solve certain geometric invariant theory type problems, and indeed these algorithms implement well-known isomorphisms between the GIT quotient sort of and the symplectic quotient, sending semi-stable things to moment map 0, but that's only for the experts. I don't want to go into detail at this point. All right, so that was an excursion. Okay, I want to show you some more examples where tensors and different actions So the action on tensor tuples and this conjugation and simultaneous conjugation and simultaneous multi-conjugation action, but they are relevant. Now I want to return to quantum states. Here again, our protagonists, okay, the tensor action, and we'll stay with quantum states for the rest of the talks. This was really just an excursion. Here are our protagonists. If you have a tensor T, we can get a new one by applying this tensor action. And the quantum marginals, they were these positive semi-definite operators obtained by contracting or by as the Gram matrix of your J's principal flattening, or if you like, as a split. So before, I mean, the key idea behind the normal form of 2001 was to make these morphs uniform. Okay, and generically we can do it, but often we are not interested in generic tensors when we want to study delicate properties of specific tensors. And so, for example, you could ask, well, if I cannot get to the uniform point where all the marginals are uniform, what are the marginals I can actually get? Okay, what are the relations? What are the constraints? Relatedly, you could then try to use such ideas to define normal forms or invariants that also make sense for unstable tensors. Okay, so the normal form before just didn't give you anything. Well, the normal form was the zero tensor. Okay. All right. So, in other words, what we would like to understand is the following object. Suppose you take your starring tensor T, you look at all the generations of it, normalize them to norm 1 just for definiteness, so that things are happily normalized. And then from this S, compute all of the marginals, put them into a big list. Okay. You want to understand this set. Now, because the group action is closed under unitaries, unitary on N1 times unitary on N2 and so on, we can characterize the set without writing down all of these matrices. The only information that's interesting is spectral. So what are the eigenvalues of sigma 1, what are the eigenvalues of sigma 2, and so on up to the eigenvalue of sigma d. Okay. So we can define a reduced object, which is the following. So again, same as before, we take arbitrary degenerations without loss generality of norm 1. We compute these marginals, and now we look at the spectrum. Spectrum in the sense of matrices, eigenvalues, sorted set of eigenvalues. Okay. Because we do norm 1 here, these turn then out to be to sum to 1, these eigenvalues, because the sigmas are positive semi-definite, the eigenvalues are large equal to 0. So each of these spectra are probability distributions. So it's a long vector that's a tuple. Each element of the tuple, the J's tuple, is a probability distribution on nj many outcomes. Okay. We can collect all of these things into an object I will call delta of T, and that has been called the entanglement polytope. And what's not obvious at all but true is that it's really a polytope. Okay, and it's sort of a hard proof from the 80s. In this setting, goes back to Mumford's appendix to a paper with Linda Ness and Kirwan in the smooth setting proved similar things. Okay, so it's a version of famous convexity theorem, symplectic geometry, to which actually somehow we now know much more, let's say, concrete and quantitative proofs than back in the day. So it's not just importing, but it's non-trivial polytope. Yeah? So that's kind of interesting. So here's the same polytope again, just recall the definition. I show you two examples in the lowest non-trivial dimension, which is C2, C2, C2. I'm not sure if these pictures were already there. Certainly the tensors were there. So this is the tensor that's E0, E0, E0 plus E1, E1, E1. It's called the GZ state, level 2 GZ state. That's what was called the W state, 1, 0, 0 plus 0, 1, 0 plus 0, 0, 1. Okay, where EIJK is the I tensor EJ tensor EK. And again, the quantum people, they write a flag instead of an E. Okay. So it turns out that these two tensors, they have different polytopes. It's known that the orbit of this guy is dense, so that's also the maximum polytope. Okay. That one is a special one. It's an unstable one. Okay. And it's a subpolytope. It's like two tetrahedra. That guy is the upper tetrahedra. Okay. And I want to emphasize that this polytope, it's non-trivial. Okay, I should explain the coordinates, but maybe I don't. Okay, so there's two eigenvalues for each marginal in that case because the dimension is 2, but they sum to 1, so I plot the largest one. So it's the largest eigenvalue of sigma 1, sigma 2, sigma 3. That's a 3-dimensional space. So the origin is 1/2. Okay, it's not 0. Now, I want to emphasize that even for generic T, it's non-trivial to determine these objects. For example, these facets here in the interior, even though it will not be easy to see when you look at it the first time, they are not implied by the fact that these are probability distributions. But the trivial inequalities are saying, okay, the P's are all large equal to 0, they sum to 1, and P1, the first eigenvalue is large equal to the second one because I sort these, right? So for me, the spec is a sorted vector of eigenvalues. So there's always a trivial ordering, which are inequalities, okay, bounding your polytope. But those are more these coordinate walls. Okay? The interior ones, they're interesting. Okay? So even for generic T, or if you don't fix T at all, if you just ask what are all the possible marginals of quantum states in a fixed dimension, kind of marginal problem, as was mentioned in Tonia's talk, in a very different setting, this is not trivial and non-trivial to complete. Now let's discuss some properties. First of all, the uniform point. Okay, here I normalize to norm 1. So instead of getting identities, I get normalized identities to trace 1. So the all ones vector, sufficient normalized in this polytope, is the case if and only if I can degenerate to marginal sigma j proportion to the identity matrix. And as we discussed, that's exactly, well, by definition, when it has a normal form in the sense of Frank and friends. And we discussed that that's the case if and only for a tensor semi-stable. So you can detect semi-stability by the fact that this origin corresponding to identity, normalized entities in the polytope, so semi-stable, unstable. Okay, for algebraic folks. Now, the second thing is that, of course, this object is G invariant, right? Because if you apply G and then afterwards you compute the orbit or the orbit closure, that's of course does not only depend on the orbit. Okay? So it's some kind of invariant, but it's like a polytope valued invariant with respect to this action. And if you ask, well, how does it behave with respect to closure? Of course, it's monotonic, right? If you take a vector in the orbit closure, if you take a tensor S that's in the orbit closure of T, then it might be its own orbit will in general be a proper subset, so you get fewer marginals from it. Okay? So the polytope associated to something in the boundary of another tensor is never larger, generically smaller. Okay? So that's interesting. Okay, so for example, one can now define entanglement measures or tensor parameters, as we'll call them in a moment, by maximizing or minimizing functions over this polytope. Okay, if you maximize your favorite function over the polytope, and then your polytope becomes smaller, the max will be never larger, right? So this monotonicity of the polytopes is then, of course, inherited by any maximization of any scalar function. So you get, if you like, a whole family of monotones. Okay? And the question is, what are interesting? Monotones are in the sense of quantities that never increase under degeneration. It's decrease, or well, it depends on whether you're max or min. All right, so I want to discuss to you a second perspective that has in fact motivated and driven much of this developments in figuring out, exploring the structure here. Okay? And that's by regarding tensors not as quantum states, but as computation problems, which is probably also something that has been already, well, I guess, several talks are certainly motivated by this perspective, maybe tackling it with different methods. Here is one, okay, just to remind you. So here are two computation problems and the corresponding tensor, so definition by example. Suppose you want to model the problem of multiplying R many numbers. It turns out that a useful way of capturing this, okay, that's a bilinear operation, okay, a useful way of capturing this is by this object here, which people call the unit tensor of rank R. Okay. It's like a generalized diagonal matrix or identity matrix, if you want, to the tensor set. Okay. You can imagine, right, like it picks sort of, if you think of it as a bilinear map from two tensor factors to one, well, bilinear map, it picks out the j's coordinate of the first input of the second and multiplies into the j's output of the output vector. Here's another tensor that we already saw. This is called MAMU earlier on. It's a structured tensor of matrix multiplication. So if you have two n by n matrices, the product is again n by n matrix. So each tensor factor is now n squared dimensional. And Eij for me is an elementary matrix, IdIj elementary matrix. Okay, and then people with better taste than I maybe revert the Ki, the Ik to Ki. Okay. So you can. So these are two tensors. Okay, they're concrete tensors. The left one is in CR, CR, CR. The right one is Cn squared, Cn squared, Cn squared. You can pad them if you want to be in the same space. And you could ask, well, what is the relation between these things? And the interesting observation, and all of this sort of going back to Strassen, is that reduction in the computational complexity sense between computation problems corresponds in a certain precise way to restriction or degeneration, depending on what you ask, of these tensors. For example, if you would like to know what is how many multiplications do I need to multiply two n by n matrices, it's related to converting this tensor to that tensor by this action and its potential limits. So the complexity in this algebraic sense of matrix multiplication, for example, is captured by the following object. Let's look at large n by n matrix multiplication tensors. Let's ask what is the smallest unit tensor so that I can get from here to there. And then you basically look at this ratio, log r. So that's kind of counting in an extensive and an additive way how much worth of unit tensor you have. And that's how much worth of matrix multiplication. For example, imagine R is a polynomial, right? So, like we know, high school multiplying matrices is n cubed, right? So we expect R as some polynomial, something. So the exponent, let's call it omega, something between 3 and 2. Right? Then there's log n to the omega over log n would be omega. Okay, so that's the reason for scaling. Slightly different way of doing it is one can observe that k copies of this guy is another unit tensor of rank or dimension r to the k. Okay, so in fact I can slightly rewrite it. I can set r to be 2 to the k and n to be 2 to the l. And now it's an asymptotic question. It's basically asking, this should be a little bit L goes to infinity, sorry. If I want to produce many copies of the 2 by 2 matrix multiplication tensor, how many copies of the standard GHZ state, the standard unit tensor of rank 2 do I need? Okay, and that's the ratio of copies. So same. This picture makes it really clear. It's an asymptotic question about conversion of 2 fixed tensors. Okay. All right. So to discuss such conversion type questions, okay, motivated, for example, by the algebraic complex matrix multiplication, people have, I mean, this is a hard problem, right? I mean, many people are here proving lower bounds and upper bounds, all these things. So one approach that people have done is to define, let's say, simpler parameters that are maybe one can hopefully bound and then maybe a particularly well behaved, especially with respect to these asymptotics. So here's one way, and the reason I'm telling you about it is because it's directly defined in terms of this entanglement polytope from before. Okay? So here is how the definition goes. So it's called the quantum functions because it's defined using quantum things, okay, using this quantum mindset. Let's maybe start with a light blue here. So theta is just it's just a probability vector that weighs things. Think of theta as being 1 over d. It's not important. I have to write it down. So what is this doing? Okay, so you're taking arbitrary point in the entanglement polytope. It's a tuple, right, containing the eigenvalues of the j's marginal in its j's entry. I call it xj. Xj, I told you, is a probability distribution, so you can compute its entropy. So here's the Shannon entropy of a probability distribution, just to remind you. So you compute the entropy of each marginal, and then you weigh it, okay, with these weights theta. Again, think of them as uniform. So it's like an average entropy of the marginals, okay? And now you simply maximize this over the whole entanglement polytope. So that seems like not something that, well, maybe if one knows this Strassen's theory and how entropy appears, then it is natural. A priori, it seems maybe surprising that it's sort of on the slide following the ones on algebraic reductions. Okay, so that's the definition. And then because entropy is sort of additive with respect to tensor graphs, one takes the power and log is space 2, and for me, so it's the 2 to the something. That's then this quantum function. Okay, so it turns out that if for matrices, that's just a rank. It's just a complicated rank because the 2 tensor like this will always be maximized when things are uniform, and then the entropy is just the log dimension, the log rank. For higher dimensions, this is not the tensor rank. Okay, it's some other quantity. And what's really cool and very non-trivial is that this object, which is defined in terms of one copy of the tensor, right? It's like one tensor. It has this polytope describing its marginals. You maximize entropy over it. This object is multiplicative with respect to tensor of tensors and additive with respect to diagonals. Okay. So what do I mean by multiplicative? If I have 2, 3 tensors, for example, I can tensor them together. Now it has 6 indices, but I can group them again together, such that the first index of the first copy and the first index of the second copy are one big index. Okay. So I can think of this again as a 3 tensor. But now, of course, I have a bigger symmetry group, right? Now it's n1 times n1 prime, and 2 times n2 prime, and 3 times n3 prime, and a different polytope and so on. So like very non-trivial. Principally, the polytopes will not be the same. Nevertheless, if you compute this quantum function of t prime tensor t prime, it's going to be the quantum function of t times the quantum function of t prime. So that's very surprising, okay? And it's directly useful to bound these conversion rates. So, for example, if you want to, why is that the case? Well, if you care about converting k copies of t to l copies of s by S losses c, for example, right? You know that. For example, this e quantity of this f quantity of a tensor power is f of t to the k. If you take the logarithm, the k goes to the front. Okay, and you get these logarithmic quantum functions, the e's. And so the conversion rate, okay, can directly be lower bounded by this ratio of these quantum functions, by these logarithmic quantum functions. Okay, so that's why it's interesting. So that's also related to these, questions that we discussed in this morning's. So, for example, it shows that the quantum functions are sandwiched between an asymptotic rank, example, okay, for experts. That's kind of the special case when one of the two is a unit tensor. All right, so the quantum functions are one example of tensor parameters that can be defined by optimization over this polytope. Okay, so we have this mysterious entanglement polytope. We can optimize functions. Quantum functions are obtained by maximizing entropy. You can pick other functions to maximize or minimize. Okay, if you want to maximize concave is nice. If you want to minimize convex is nice. Then it's a convex problem because your object is a convex polytope. Okay, so quantum functions were one example. Then Harm has introduced the so-called G-stable rank in a more general setting. In the complex case, you can reduce it. I'm being vague here. I don't write down a precise formula, but it's related in some sense to the largest eigenvalue instead of the entropy of these components. Okay, there's an object called the non-commutative rank, which one can relate in another way. I will not go into the one norm. Okay, the sum of the singular values. Then the L2 norm is also natural, but I will not go into it here. And then, of course, instead of looking at tensor with this symmetry cube, you can look at symmetric tensors and antisymmetric tensors, and all kind of variations. So there's a zoo of tensor parameters that are defined in the end. I mean, either by their definition or in hindsight as optimization problems over this polytope. Okay? And so one recent result with Kea, who will speak after me, and Leon Duan, is that we now manage to find algorithms for all of these. Okay? And for example, for these quantum functions where you optimize entropy, you get a scaling type algorithm. We call it entropic tensor scaling because it's maximized entropy. That has a similar form as what Frank did. Okay, so Frank had this procedure, or Frank and Course had this procedure where they looked at one margin at a time, making it uniform. Okay, here you act on all of them at the same time. Okay, and these theta, I remind you, that is the weights. Okay, in your the weights in the definition of quantum functions. So just imagine the theta of 1 over d. So then this is the inverse 2d's root. You do all of them at the same time. Has nice properties. Like if you're tensor symmetric, then it stays symmetric because all the margins are the same and so on and so forth. It's also structure interesting. For example, it gives to let's say our taste maybe the simplest proof that these quantum functions actually satisfy these non-trivial properties, that they're multiplicative and additive. For example, multiplicativity basically follows from the observation that this simple iteration computes the value of the quantum function, but it also preserves the structure of the tensor. If the tensor is a Kronecker product, if S is S prime, tensor is double prime, then that's preserved by the algorithm. So you will find a maximizer that's actually in the orbit of the subgroup, and that basically is the proof. Okay? So previous proof was not so complicated. It proved this inequality by representation theory and smart considerations. Okay? All right, so of course, these different parameters, they're only interesting if the tensor is not semi-stable, because otherwise the origin is the maximizer and it doesn't really matter what you maximize. Okay, so I want to tell you in the remainder of the talk a little bit about how this is approached, what are the ideas. So I want to briefly talk about the classical problem about the general problem of maximizing or minimizing functions over polytopes. Okay? So entropy is concave. Here I want to look at the convex function, so I'm going to minimize over polytope. So that's a nice convex problem. That's been studied maybe since the dawn of time. Here's a polytope. And if the polytope is given to you explicitly as a list of vertices or a list of facets, then it's very standard to do. Okay. However, in many applications, also in the case here, this polytope is not given to you explicitly. Right? Was like a difficult theorem by Kirwan and friends that it's even a polytope. So that also, but it turns out that in that case, if your polytope is implicitly defined, sometimes one can still solve these problems. Okay, or in other cases, when it is explicitly defined, but in an exponentially complex way, like in the sense, it's, for example, the polytope spanned by an exponential number of points, then it's not a good idea to use that exponential description. You want different ways. So the base polytope of matroids is an example from combinatorial continuity. Yes.
But in this case, unknown, right?
So it's a continuous set respect of these marginals. So it's kind of for every tensor in the orbit, you get 1 point, and it carves out a polytope. But it's not a priori clear what the vertices are. So the set, right? It was not the convex. I mean, it's also the convex hull, but sort of the here. So this is a continuous set of S's, right? And so it's infinitely many objects, and it's in big. Okay, there's and because there's closure, it's maybe not even maybe the vertices will typically correspond to degeneration, so it's kind of non-trivial. And now, I mean, we know different ways and different settings of computing it, but it's in general a hard problem. Like even for 3x3x3, we wrote a long paper with Maxime last year to work all of these out. Okay, and that's a setting where the orbits are known and so on. So it's it's interesting. Thanks for the question. So I want to give you an example that's sort of a classical Euclidean analog of what underlies the structure here. Okay. So here it goes. Suppose you want to describe a polytope, and now it is actually given. I mean, it is just a convex hull of a bunch of vertices. I call them omega j. I now want to describe the same polytope in a different way. So the way I want to do it is as follows. Just calibrate, very good. The way I want to do it as follows. Let's take these omegas and build a convex function, build a function. Okay, this function, people call it a log sum x function because the log of the sum of exponentials. It's a function of Rn, whole of Rn, and it's exponential of x variable dot this point omega j. Now, it's not hard to see that the gradients of this function are convex combination of the omegas, right? Because the gradient pulls down the omega j, and then the log makes it such that it's normalized to sum to 1. So every gradient is a point in this convex hull. And it's not so hard to see that the closure of the gradient set is actually the same as the convex hull. So one way by which I could give you a polytope is by giving you such a function. Maybe I will not write it down, of course, in this way, especially if there's exponentially many j's. I will just maybe give you an algorithm or a formula or some mathematical description of this form. And then the question is, can you solve interesting problems about the polytope given access to this function? Okay. So you could say that the polytope is sort of succinctly encoded, well, if f is somehow a succinctly described function, is the set of gradients of this function. Okay. And so basically what I want to briefly show you is that the same structure also applies to these entanglement polytopes. Okay, so there's a way of thinking about this entanglement polytope essentially as gradients of a function in a slightly more complicated setting. Okay, here I want to emphasize this function f is convex. Okay, and that's important for this gradient set to be convex. So we can come back to this in a second. So maybe this is the last thing one of the second to last slide I want to show you. The claim is that we, in a way that's very analogous to this log sum x function, one can associate polytopes to any nice group action. Okay, and so, for example, for the entanglement polytopes, of course, the group action is the tensor action by a product of GLNs on the space of tensors. So, what does this generalization of the log sum x function look like? Okay. It needs one ingredient. So, let's suppose we pick a tensor t. We're now going to define a function that should somehow encode this polytope of t, this entanglement polytope of t. What is the domain of the function? The domain of the function I take as the positive definite elements in this group. So PDN1 times PDN2 and so on. Times. And the function is, well, it's a log sum exponential somehow in the right basis. Okay, so it's a log of the inner product t and then the tensor action, but restricted to these positive guys, applied to t. You can think of this as simply a norm, similarly in how Frank's algorithm minimized the norm. A norm of taking when you take your tensor and you apply the square root of p as your group element, right? The norm squared then gives you twice the square root, which is just p itself. So these are the same things. And it's now not so hard to verify that if you compute the gradient of this function f, it's basically computing these marginals. The idea is that it's a bit, you do product rule, so it's one p at a time, and the other p's are fixed. So what you get is the marginals not of t, but the marginals of the rescaled tensor, something in the orbit. Okay, so as you change p and you compute the gradient, you basically carve out all of these marginals, and there's some slight twist because of this multiplicative way, there's an inverse floating around here, okay, which has a meaning, but maybe it's not so important. So the point is that you can access the quantum marginals again as gradients of a function that's like a log sum x function defined in terms of the group action. Okay? And I wrote it down intentionally so that it looks maybe the generalization of this picture. So here's again the same setting. Okay? So we have our function f. It's this generalized, log norm, log inner product, log sum x function. Why do I say sum x? Because I can diagonalize this positive definite group element p and work in the eigenbasis. Then it's literally a log of the sum of its branches. It's defined on this domain. So what do? I compute the gradients. I have to do this little twist by the square roots to get the actual marginals and not the what I wrote before. Then I compute the spectrum of each entry, and that's exactly the same definition as the polytope before. So basically, we have encoded our entanglement polytope as the gradient set of another polytope. Okay. So the sad story is that while this set is a convex subset of the Hermitian matrices in the usual Euclidean sense, this is not a convex function. Okay. That's a sort of annoying multilinear feature. However, it is a convex function in a different way. Namely, if we think about the set of positive matrices as with a different geometry, it's called a fine invariant metric. It's a metric where the geodesics take this form. Okay, so instead of being straight lines, p plus x times t, they are these given by the matrix exponential. Okay, in this way, square of p e to the xt square of p. So that's a curve that at t equals 0 is p. So it's a curve through p. Okay, but it's not a straight line in the Euclidean sense. Okay, so it turns out that these are geodesics for a very well-known metric coming from this corresponding symmetric space, which is non-positively curved. Okay, and with this in mind, we can actually interpret this formula in a nice way. It turns out that the square root stuff is just doing the parallel transport. It's taking this gradient, which is at a point p in the manifold, and moving it to the identity, which is of the common reference point. Okay, and if you do this, you get these, just get the ordinary margins. Okay, so I will boldly do this and then conclude. So the punchline of this approach, and all I want to say is, we started by optimizing over this entanglement polytope, this implicitly defined polytope. For example, phi was the Shannon, the sum of the Shannon entropies of the marginals, and the delta of t was the polytope. Now we write this in different variables. We go to this new space, we parameterize our polytope in terms of gradients, okay, of a new function. This is this function whose gradients give us the marginals. Now we still have this annoying thing that we should compute the eigenvalues. So how can computing eigenvalues is not a nice thing that you want to do in life. So how can you do it? One way of doing it is to extend your functions on probability distribution, the Shannon entropy, to a convex or concave, in that case, function on the marginals. Okay, so that's going from the entropy of probability distributions to the entropy of quantum states. Okay, and that is then the setting. And so in this setting, Kea will in a moment explain how we then analyze these algorithms. Okay, so that's the idea. So I will skip some more technical stuff here, which told you how to derive these functions and conclude. So the pitch of the talk was, well, we all love tensors because they appear in many different places. I emphasize two: the quantum perspective and the perspective of these algebraic complexity problems of algebraic complexity. There were group actions that we either liked because we wanted to ignore them and look at normal forms, or because they were natural symmetries of our problems. So they gave rise to interesting marginal problems and polytopes and quantum functions. And the pitch was that we can characterize them by methods, by optimization methods, okay, convex optimization methods, and which allows to effectively access these implicitly defined polytopes. Okay. So with this, I thank you for your attention.
Thank you for the very nice talk. We will back for your questions. I think you solve this optimization problem using a command SOS.
Yeah. So partly, yeah. So for example, I'm aware of at least one paper that So for example, if you look at this marginal problem, and let's say you don't care about the starting point, so you just ask what are the compatible margins, right? Then somehow the marginals, they are a linear function on the density operator on TT star. Okay. But here the state is a pure state, so it's like a rank 1 type thing, right? And so you can do a realization either in sort of a hands-on way or systematically by a polynomial optimization problem. And then use similar tricks as one does for separability testing, for example, where you also have to enforce products, factors, and so on. You can also approach that. It's not so. Maybe there's two aspects. I mean, one is that it's not so easy to have, as I don't think people have given quantitative guarantees in that setting. although maybe one might, because it's a pretty concrete setting. For these entanglement polytopes where T is given, I have not seen this approach being carried out. But it's a good question. I mean, somehow the algorithms we have here, they're polynomial in some parameters, but for example, in the precision, they're exponential in the worst case. Okay, so it is interesting even to have an exponential time bound, like some quantitative bound for other methods, for example, like an SOS type approach. That would also be interesting, I think. Thanks for the question.
In the very beginning, you had like the restriction of T to S. Was something like S equal A1 to AD times T.
Yes.
And this looks exactly like another tensor decomposition, namely the packet decomposition. I wondered if
decomposition. And remind me, Tucker, it's not ADS tensor trains, no?
It's like there's the center, you have the central tensor T.
Yeah.
And then you sort of add that it's a star decomposition, not one line.
Yeah.
Sort of your graph is a star.
And what is the reduction in complexity in that case? Like the middle guy is small?
Well, the middle guy is like big, like core tensor or whatever, and then the A's are sort of redundant information from different data slices. And I just wondered if this is the restriction from S to T or the other way around, then and this looks like a subspace of packet decomposition, then you do the same restriction with other type of tensor decompositions.
Yeah, good question. So, yeah, so I'm always confused about the terminology in the numerics community, so hopefully I'm addressing the right decomposition. So I do know that I think in some United folks, I think I've also looked. I think it's an iterative packet. Like there's some name I forget. But is it your again? Yeah. So that's the tree one. Also, even this one I thought had maybe there's no prefix. Okay. So I've seen this. I'm not aware of convergence bounds or things in that case. But I mean, certainly one can interpret it this way. For other decompositions, so I think trees are potentially interesting because you have, from an algebraic perspective, there's a subgroup chain, so one could conceivably do things. I don't think it has been done. Certainly not from this perspective.
And then more general, like the subset would be based on tree.
Yeah, right. I mean, here the nice thing is that it's like one layer and the A's they compute with each other. So one thing you could imagine possibly is like like for tree, what I imagine is maybe you repetition, then you fine grain more and more. That's how I would let's say think of a tree tensor network. I gave another example before where the group action was a bit different, but that gave connected to the tensor trains, right, to MPS. So that one the approach is here, I would say. For tree tensor networks, I don't think this has been carried out yet. There's related problems that maybe we can talk more offline.
Then let's figure it.